Hello, ChE 191 students. I am Eliezer L. Vivas, a PhD student of the Laboratory of Particle and Sustainable Technology at the Department of Environmental Engineering of Pusan National University. In my final lecture, I'm going to share with you our latest research publication entitled Brushite-infused polyacrylonitrile nanofiber adsorbent for strontium removal from water. At the end of this lecture, you should be able to describe why brushite and polyacrylonitrile nanofiber were chosen as the inorganic adsorbent and polymeric support respectively. Differentiate the three classical models of equilibrium adsorption isotherms and the reaction kinetics models. And explain the influence of pH, initial concentration, and time on the adsorption performance of the composite nanofiber adsorbent. This will be the flow of my second lecture. This graphical abstract highlights the following. A polyacrylonitrile dicalcium phosphate dihydrate nanofiber was first fabricated. The nanofiber composite adsorbent exhibited good strontium uptake in water with a maximum adsorption capacity of 146 mg per gram. The composite nanofiber adsorbent removed at least 80% of strontium ions in water, and that this composite nanofiber can be used as a microfilter for the adsorptive filtration of radiostrontium. Radiocontamination of water is a global concern. The Fukushima Daiichi nuclear disaster and the decommissioning of over 100 nuclear reactions worldwide led to the increase in the demand for efficient water treatment technologies to remove radionuclides such as strontium-90 or radiostrontium. Strontium-90 is considered the most toxic among the nuclear fission products because of its high solubility, longevity, high transferability, bioavailability, and easy bioaccumulation. Possessing calcium-like biochemical properties, strontium-90 is readily deposited in the bones and teeth, which can cause cancers of the bone, bone marrow, and soft tissues around the bone. It can also cause genetic mutations in plants. Hence, its removal from water is a primary concern, as water can easily carry and incorporate it into the tissues of living organisms. The best available small system technologies is compliant with the United States Environmental Protection Agency implementation guidelines for radionuclides for strontium-90 removal from water are ion exchange, reverse osmosis, lime softening, enhanced coagulation or filtration, green sand filtration, co-precipitation with barium sulfate, electrodialysis or electrodialysis reversal, preformed hydrous manganese oxide filtration, and use of activated alumina. Nevertheless, alternative treatment systems or techniques that can meet the maximum contaminant concentration can be explored and applied. Adsorption, which I have discussed in my previous lecture, is considered as one of the most effective strategies in removing toxic heavy metals from contaminated waters, owing to its simplicity, low cost, selectivity, efficiency, and wide adaptability. Here are the representative adsorbents which were investigated for the removal of strontium from water. Owing to the bone-seeking attribute of strontium-90, calcium phosphate minerals found in human bones have become promising adsorbent candidates for strontium-90 sequestration from water. Hydroxyapatite, or HA, the main calcium phosphate bone mineral, has been widely investigated for strontium removal from water in its pure, modified, and composite forms. Brushite, which is commonly known as dicalcium phosphate dihydrate, or DCPD, is another calcium phosphate bone mineral that can be considered as a potential strontium adsorbent. DCPD is a malleable monoclinic bioceramic with lower surface energy, faster nucleation rate, superior resorption rate, and excellent biocompatibility in comparison with other calcium phosphates. It is extensively studied for biomedical applications, especially in the production of bone graft materials. DCPD has been less explored for the removal of toxic heavy metals from contaminated environments due to its relatively lesser stability. Nonetheless, DCPD could perform better than hydroxyapatite and other calcium phosphate adsorbents in terms of divalent metal ion adsorption and retention, because its lamellar structure provides more free interspaces. This implies that DCPD could be superior in sequestering strontium ions in water. Powder DCPD was successfully used in the removal of zinc and copper ions from water. It was also applied in the removal of fluoride from water. However, the field application of DCPD for the removal of any pollutant from water is limited because their recovery after use is challenging. In my first lecture, I highlighted that most adsorbents are in powdered form, and due to this, they are prone to particle loss, making the recovery process from an aquatic system upon saturation quite challenging. This separation difficulty adversely affects the practical application of any powdered adsorbent. Hence, for a more favorable and manageable adsorption of strontium using DCPD from water, immobilization of DCPD powders in solid supports is a potential solution. Here are some examples of powdered strontium adsorbents which were immobilized in different solid supports. The researchers were successful in immobilizing the strontium adsorbent powders. However, the composite adsorbents exhibited relatively low adsorption performance in terms of strontium adsorption capacities. If you would see, the strontium adsorption capacities of these solid supported strontium adsorbents were below 100 mg per gram. The use of nanofibers as a solid support for powdered adsorbents has gained a considerable amount of attention in water treatment, owing to the following features. First, large surface area to volume ratio that can provide higher accessibility of adsorbent sites to the target pollutant. Second, nanofibrous morphology that is favorable for the protrusion of adsorbent particles on the fiber surface, which increases the exposure of binding sites. Third, high porosity achieved through micro to macro scale interfibrous spaces that can accelerate the convective diffusion of the target pollutant from water. And lastly, favorable mechanical properties that can prolong the useful life of a pure or composite nanofiber. The research question for this study was, how can strontium adsorption in water become more manageable using DCPD adsorbent powder? The hypothesis was, if DCPD particles were to be immobilized into a web of polymeric fibers, then strontium removal in water would be more manageable, meaning we would minimize or prevent particle loss, and it would lead to the production or fabrication of environment-friendly composite adsorbents. Polyacrylonitrile nanofiber, or PAN-NF, has demonstrated promising performance in terms of immobilizing adsorbents owing to its excellent wettability in water, favorable mechanical and thermal properties, and high chemical resistance. PAN-NF does not require post-treatment, unlike water-soluble nanofibers such as polyvinyl alcohol, which require thermal or chemical cross-linking to prevent dissolution in water. In view of this, PAN-NF is the best candidate in immobilizing DCPD adsorbent powders for the removal of strontium ions from water. Per my first lecture, electrospinning is a simple, readily available, effective, and widely used technique to transform polymer solutions or melts into nanofibers with an average fiber diameter of less than 1 micrometer or within the fiber diameter range of 50 to 500 nanometers. By fine-tuning the electrospinning parameters, PAN nanofibers with a desired morphology can be fabricated. This slide shows the preparation of DCPD powders and the fabrication of pure and composite PAN nanofiber adsorbents. DCPD powders were prepared via wet chemical precipitation synthesis. Aqueous solutions of 0.40 molar calcium nitrate tetrahydrate in 0.68 molar hydrochloric acid, which we will call solution A, and 0.24 molar diammonium hydrogen phosphate in 0.70 molar sodium hydroxide, which we will call solution B, were prepared by dissolving the necessary reagents in the ionized water at 500 rpm for 30 minutes. Solutions A and B were then refrigerated overnight at 5 degrees Celsius. An Erlenmeyer flask with solution A was then placed in an ice bath and continuously stirred at 300 rpm. Solution B was added periodically to solution A at 10 ml per minute. The resulting heterogeneous mixture was stirred at 500 rpm for 5 minutes and then refrigerated for 24 hours at 5 degrees Celsius. The aged DCPD precipitates were then separated from the supernatant and rinsed twice with the ionized water through a Combi 51 4R centrifuge, operated at 10,000 rpm for 10 minutes. The precipitates were then oven and vacuum dried for 2 hours at 60 degrees Celsius and 24 hours at 100 degrees Celsius respectively. The dry DCPD product was pulverized with agate mortar and pestle, screened using a standard test sieve number 200 with a 75 micrometer aperture, and then stored in moisture-free glass vials. A dope solution of 10 weight% PAN in N-dimethyl formamide, or DMF, was used to form pure PAN nanofibers. PAN solution was magnetically stirred at 700 rpm for 8 hours. 4 hours at 60 degrees Celsius, followed by 4 hours at 25 degrees Celsius. The composite dope solutions were prepared in a similar manner. Pre-weighed DCPD powders were dispersed in DMF, heated at 60 degrees Celsius for 2 hours. An appropriate amount of PAN powders were added and continuously stirred while heating at 60 degrees Celsius for 4 hours, and then equilibrated by stirring at 25 degrees Celsius for another 4 hours. A 10 ml polypropylene syringe with a 0.51 mm inner diameter needle was filled with a dope solution and fed into the syringe pump of the electrospinning system at a constant flow rate of 4 ml per hour. The tip-to-collector distance employed was 100 millimeters. To obtain a uniform mesh thickness, the aluminum foil wrap rotating mandrel collector was rotated at 490 to 500 rpm. The applied voltage was maintained at 21 to 23 kilovolts to expel the dope solution from the tip of the spinneret into a web of nanofibers. The electrospun mesh of nanofibers was collected, covered with aluminum foil, vacuum dried at 60 degrees Celsius for 12 hours, and then stored in a moisture-free plastic zip bag. The mesh was then cut into pieces of desired shapes and dimensions, and peeled from the aluminum foil before its use in further experiments. Listed here are the different material characterization tests performed. This shows how the adsorption experiments and analysis of samples were conducted. Strontium ions from the dissolution of strontium chloride hexahydrate in the ionized water served as a surrogate of radiostrontium. All adsorption experiments were conducted in batch mode at 25 degrees Celsius or 298 Kelvin. At a solid-to-liquid ratio of 2 grams per liter, dry pre-weighed DCPD powders, pure PAN nanofibers, and PAN DCPD nanofibers were soaked in 20 ml aqueous strontium solutions and agitated at 200 rpm for 24 hours using an orbital shaker. The effect of the initial solution pH on strontium uptake of the adsorbent materials was investigated by performing the adsorption experiments at different solution pH values for a 500 mg per liter or 500 ppm aqueous strontium solution. Drops of 0.5 molar NaOH and or 0.5 molar HCl were added to the aqueous solutions for pH adjustment. Subsequent adsorption experiments were conducted at the optimum initial solution pH. The effect of DCPD loading, 10 to 98%, on adsorption capacity was evaluated using 500 ppm aqueous strontium solution. The PAN DCPD-NF with the highest adsorption capacity was used in the succeeding adsorption tests. Equilibrium adsorptions were conducted at different initial strontium concentrations of 10 to 500 ppm. The effect of initial concentration on the removal efficiency was evaluated using an equation that will be discussed later. Kinetic uptake studies were also conducted under the same conditions, but with initial concentration at 10 mg per liter. To evaluate the influence of competing metal ions on the selectivity of PAN DCPD-NF for strontium uptake in terms of distribution coefficient or KD, adsorption using strontium spiked artificial seawater or ASW was performed. PAN DCPD-NF was also employed as a membrane for the dead-end adsorptive filtration of strontium ions. A subtuple PAN DCPD-NF membrane with an effective diameter of 25 mm was mounted on a polypropylene filter holder. The membrane assembly was then connected to a polypropylene syringe with aqueous strontium feed, or initial concentration of 10 ppm. The feed was delivered at different flow rates of 0.05 to 0.2 milliliter per minute using a syringe pump. The same procedure was used to evaluate the adsorptive dead-end strontium filtration performance of pure PAN nanofiber. The collected permeate samples were analyzed for strontium concentrations to calculate the removal efficiencies. Liquid samples before and after adsorption were transfer filtered in sample tubes using 0.2 micrometer cellulose acetate syringe filter units. Aliquots of the collected samples were diluted into aqueous solutions containing 1 times 10 to the 3 milligram per liter or 1 times 10 to the 3 ppm potassium ions from potassium chloride and 2.58% nitric acid or HNO3 in polymethylpentene volumetric flasks. Strontium concentrations were determined via flame atomic absorption spectroscopy. Portions of the collected liquid samples were allotted for pH measurements using an Orion Star A211 pH meter. and the remaining raw samples were stored in a cooling chamber. Here are the equations used for the calculation of adsorption capacities, removal efficiencies, and the adsorption capacities of the samples at different contact times. The selectivity of the composite nanofiber adsorbents for strontium uptake in terms of distribution coefficient or KD was calculated using this equation. The models for the equilibrium adsorption experiments were Langmuir, Freundlich, and Sips. I believe you are familiar with the Langmuir and Freundlich models. The Langmuir model describes a monolayer adsorption process, while the Freundlich equation or the Freundlich model describes a multi-layer adsorption. I think you are not familiar with the Sips model. The Sips model is actually the combination of the Langmuir and Freundlich models. It describes a heterogeneous adsorption process. It means uptake of any pollutant is not limited to monolayer adsorption. The influence of time on strontium adsorption capacity by PAN DCPD-NF with 78% DCPD loading was investigated using pseudo-first and pseudo-second order kinetic models, as expressed by these nonlinear equations. Nonlinear regression analysis was employed for the data gathered from this experiment, since mathematical linearization of these nonlinear equations could result in biased approximation of constants and hence may lead to false conclusions. The XRD pattern of synthetic DCPD powder depicted in this graph exhibited an almost identical match to those reported in earlier studies, which could be indexed using the monoclinic crystal system with C1 space group. The computed lattice constants A were in good approximation with each other and with a standard value. This demonstrates that the synthetic DCPD does not transform into hydroxyapatite or other calcium phosphate intermediates even when the physiological conditions were simulated in adsorption experiments. The results of the qualitative elemental analysis of adsorbent particles via FE-SEM-EDS depicted in this graph revealed a calcium to phosphate ratio of 1.01. The results of the XRD analysis and FE-SEM-EDS qualitative elemental analysis confirmed the successful preparation of DCPD powder through the wet chemical precipitation method. The FE-SEM images depicted or shows well-fabricated pure and composite PAN nanofibers. The DCPD agglomerates were observed in PAN DCPD-NFs with high DCPD loading. In this FE-SEM image, you would see a DCPD aggregate of more than 500 nanometer in size billowed across the nanofiber, with diameters greater than that of the nanofiber or less than 500 nanometer. Beading, which could result in an even dispersion of the DCPD particles and irregularly sized nanofibers, was observed at a DCPD loading of greater than or equal to 98%. The average diameters of the PAN DCPD nanofibers were larger than those of other composite PAN nanofiber adsorbents. A polymer in the continuous fiber form could be mechanically stronger than both membrane and film configurations, and the influence of DCPD loading on the mechanical strength of PAN DCPD nanofibers was therefore investigated, and the result is depicted in this graph. Pure PAN nanofiber demonstrated remarkable tensile strength in comparison with that of the dense PAN membrane, which exhibited poor mechanical properties. per previous experiments and related literatures. The tensile strength of PAN 10 DCPD or PAN DCPD nanofiber with 10 weight% DCPD loading was higher than that of the pure PAN. NF. At 10 weight% loading, most of the DCPD particles were uniformly distributed within the PAN nanofibers, resulting in a good PAN-DCPD interaction, thereby reinforcing the fibers. However, as the DCPD loading increased, the tensile strength of PAN-DCPD nanofibers declined significantly, owing to the increasing degree of DCPD agglomeration, starting at more than or equal to 28% loading. Large DCPD protrusions or protrusions on the nanofiber surface, which was shown in the previous slide, might have caused fiber structure defects, leading to mechanically weaker composite nanofibers. Nevertheless, no significant physical disintegration by hydrodynamic shear stress was observed for PAN-DCPD nanofibers with less than or equal to 78% DCPD loading during agitated soaking in water, unlike those with greater than or equal to 98% DCPD loading, as shown in these actual images, before and after 12-hour agitated soaking of the nanofibers. Considering their ease of handling, high adsorbent powder loading capacity, and relatively suitable mechanical strength, composite PAN nanofibers with less than or equal to 78% DCPD loading were more apposite to be applied in strontium adsorption. The effect of DCPD loading on the physical properties of PAN DCPD nanofibers are summarized in this table. Since DCPD is denser than PAN, the measured true density of the composite nanofibers increased as the DCPD loading increased. The average fiber diameter, on the other hand, also increased with the DCPD loading, as the presence of more DCPD particles made the nanofibers thicker. Capillary flow analysis revealed that all nanofibers were macroporous, with a mean flow pore diameter of less than or equal to 2.01 micrometers. All the PAN DCPD NFs were highly wettable by water. Hence, a good adsorbent strontium contact was expected during adsorption. The excellent water wettability of PAN DCPD NF with 78% DCPD loading is illustrated in this figure. A sample of PAN 70 DCPD NF demonstrated rapid water droplet uptake in 136 milliseconds. Taking into account the partial to complete dissolution of DCPD in acidic conditions, i.e. pH less than 4, and the precipitation of strontium ions into strontium hydroxide at a pH greater than 10, pH values between 6 and 10 were selected to determine the optimum pH for the removal of strontium ions from water. DCPD exhibited the highest adsorption capacity at initial pH of around 10.2. Although the composite PAN nanofiber with 58% DCPD loading demonstrated similar adsorption capacity values, the initial pH values of strontium solutions were adjusted to 10 in subsequent adsorption experiments because the DCPD adsorbent powder exhibited the highest uptake capacity at this pH level. Depicted in this figure is the effect of DCPD loading on strontium uptake by PAN DCPD nanofiber adsorbents. Pure PAN nanofiber exhibited a considerably poor strontium adsorption capability of less than 6 mg per gram. The adsorption capacities of PAN DCPD nanofiber adsorbents increased as the DCPD loading increased. The high DCPD loading led to the formation of large DCPD agglomerates, which resulted in the protrusion of DCPD particles. As a result, more surface adsorption sites of the DCPD particles were exposed and became accessible to strontium ions, resulting in higher adsorption capacity values. However, uptake capacity dipped or declined at a DCPD loading of greater than or equal to 98%, which could be attributed to too much DCPD aggregation and observed spattering of PAN DCPD aggregates out of the mandrel collector during electrospinning, hence causing self and PAN blockage of the adsorption sites, and lower presence of DCPD particles on the nanofibers respectively. PAN DCPD NF with 78% DCPD loading exhibited the highest ChE of 47.5 mg per gram and was therefore used in the succeeding adsorption experiments. Results of the equilibrium adsorption experiments showed that strontium uptake by PAN 70 DCPD-NF best fitted the ChE's isotherm, which has the highest correlation coefficient here, and this signifies that the strontium uptake by PAN 70 DCPD-NF was heterogeneous and was not limited to monolayer ion exchange. The maximum ChE's strontium adsorption capacity, or QS, of PAN 70 DCPD-NF was better than and comparable with previously investigated hydroxyapatites and other strontium adsorbents. The composite adsorbent demonstrated relatively higher strontium uptake capacity owing to two major qualities of the DCPD particles. One, lamellar structure of DCPD provides more free interspaces. And two, almost all the calcium sites in the DCPD lattice are occupiable by strontium atoms. Furthermore, a balance between DCPD loading and aggregation occurred at 78% DCPD loading. This optimum loading resulted in more aggregated DCPD particles protruded on or below across the composite nanofibers, as revealed by the SEM images in the previous slides. More exposed DCPD surfaces led to higher accessibility of adsorption sites for strontium ions, thus the high QS, or ChE's, maximum adsorption capacity of PAN 70 DCPD-NF. The calculated maximum ChE's adsorption capacity was greater than the uptake capacity at an equilibrium concentration of around 408 mg per liter. This implies that PAN 70 DCPD-NF had not reached saturation yet. Although the value of the maximum ChE's adsorption capacity is more than twice this value is more than twice of the maximum Langmuir uptake capacity. The ChE's is more acceptable since the ChE's isotherm has a steeper profile than that of the Langmuir isotherm, suggesting that the composite adsorbent reaches saturation at a significantly higher equilibrium concentration, or CE. The results of the adsorption kinetics experiments are presented in these figures and summarized in this table. This figure reveals that strontium adsorption by PAN DCPD-NF with 78% DCPD loading was a slow process, as it took 12 hours to remove 48.6% of strontium ions from water. This observation is corroborated by the computed low rate constant values for both kinetic models, as shown in this table. So look at the values of K1 and K2 here. Nonetheless, the adsorption of strontium by the composite nanofiber better fitted the pseudo-second order model, as depicted in this figure. This is supported by a larger correlation coefficient, R squared here, and narrower difference between the experimental and the calculated adsorption capacities. These results reveal that the rate-limiting step in strontium adsorption by the composite adsorbent is chemisorption, which involves the sharing or exchange of electrons, specifically through ion exchange and surface complexation. This table is a comparative summary of maximum adsorption capacities and uptake selectivities in terms of Kd values of different strontium adsorbents. Strontium uptake selectivity of the PAN 70 DCP-DNF was evaluated using strontium spiked water with pH 10 and artificial seawater with high concentrations of competing ions calcium, potassium, magnesium, and sodium. The PAN 70 DCP-DNF exhibited high and comparable Kd without the presence of naturally prevalent metal ions in water. However, its Kd drastically declined when used in artificial seawater, which had higher ionic strength than the aqueous strontium solutions. The high ionic strength of ASW probably led to the thinning of the electrical double layer, which reduced the attractive electrostatic force surrounding the adsorption sites, hence deterring the diffusion of strontium ions from the bulk solution. This implied that the metal cations competed with the strontium ions for the adsorption sites, most likely through ion exchange. Although the PAN 70 DCP-DNF adsorbent possessed low selectivity towards strontium in the presence of competing ions, its application in a post-water treatment process or in remediating softer strontium-90 contaminated water can be explored. Dead-end adsorptive filtration experiment was conducted using a membrane filter holder to demonstrate the practical application of macroporous PAN 70 DCPD nanofiber as a flat sheet membrane microfilter, or MF. After maximizing its capacity, the membrane filter holder was filled with septuple circular PAN 70 DCPD microfilters, through which the aqueous strontium feed solution passed through. The adsorptive rejection performance of the composite PAN adsorbent microfilter was compared with that of the pure septuple PAN microfilter. As the flow rate increased, the contact time of strontium with the adsorbent decreased, resulting in the observed decline in removal efficiency. The septuple PAN 70 DCPD microfilter could remove 94%, 89.2%, and 88.7% strontium ions at feed flow rates of 0.05, 0.1, and 0.2 ml per minute respectively. In contrast, the highest removal efficiency achieved by the septuple pure PAN microfilter was only 25.8% at a flow rate of 0.05 ml per minute, underlining the poor adsorption capability of PAN microfilter for strontium. Therefore, pure PAN nanofiber for strontium removal from water would be impractical and implies a waste of resources, whereas a DCPD-loaded PAN microfilter is considerably better. However, a further investigation of the combined effect of aqueous feed concentration, flow rate, and effective filtration area may improve the efficiency of adsorptive filtration using PAN 70 DCPD microfilter. Here are the conclusions of the research that I just shared with you. A potential application of a new composite nanofiber adsorbent for strontium uptake in water was successfully demonstrated. More manageable strontium removal would be achieved using the PAN DCPD nanofiber adsorbent. The fibrous adsorbent material prepared was mechanically suitable, hydrophilic, and macroporous, providing good DCPD strontium contact while preventing DCPD particle loss during adsorption. The composite nanofiber adsorbent exhibited stable adsorption performance in the pH range of 6 to 10. High DCPD loading resulted in greater strontium uptake of the composite nanofiber adsorbent as more DCPD particles were exposed on the nanofiber surface. Strontium uptake best fitted the SIFS isotherm, indicating that strontium adsorption is a heterogeneous process. Kinetic studies revealed that strontium uptake by the composite adsorbent was a chemisorption process. The presence of competing metal ions significantly reduced the Kd of the composite adsorbent for strontium, indicating a low strontium adsorption selectivity of the adsorbent material. PAN 70 DCPD nanofiber, as a dead-end membrane filter, exhibited superior removal efficiency over pure PAN nanofiber. However, further studies are required to verify the potential field application of PAN DCPD nanofiber as a composite membrane for the adsorptive filtration of strontium-90 in water. To check the level of your understanding of this lecture, please answer the following review questions. The supplemental reading material that I provided to Dr. Migo will be helpful. Thank you for listening. If you have any questions, I will be glad to answer them through email. Keep safe and healthy, okay?